Okay, let's talk about the equation. So let's start off with something simple we've already talked about, right? Equation for a line is y equals b plus mx. So remember, b is our y-intercept where our line crosses the y-axis. M is the slope, so it tells us how steep our line is. And then x is our independent variable and y is our dependent variable. So the simple linear regression model is this equation right here. So it's very similar to the equation for a line where we have y, right, is equal to beta 0. So beta 0 is the first parameter, and it's just equal to the intercept. Beta 1 is the second parameter, and it's just equal to the slope for that shows the relationship between x and y. E is the term that's kind of missing here. So E is what's called epsilon. It's the error term, and it is a random variable, meaning that it has its own distribution. What it does is it accounts for all the variable in y that cannot be explained by the relationship between an x and y. So if we think about, let's go back to our example of the pizza parlor. So we'll notice that all of the data points don't fit exactly on the line. In fact, none of them are exactly on the line. And that's because there's some error in our predictions. So let's look at this observation here. So for this school size, what's happening is that the sales are higher than what we would predict. So why? It could be that maybe there's nowhere else for the students to eat. The pizza place is the only place in town, so they have higher sales because there's nowhere else to eat. So it could be that there's another variable that's affecting sales, such as, you know, what other options students have. So if we'd included that in our regression model, availability of other restaurants, that might better help our data fit the equation or the line that we come up with. So basically what epsilon represents and stands for is that when we're trying to predict sales from student population, we're not going to do a perfect job. So any variability in y in sales that we don't capture ends up in this error term. It's kind of like a garbage bin for everything that we don't capture. But it's not garbage. Epsilon is very important. We use it actually, you'll see in some of our videos to come, it's actually very important. But just understand for right now that sometimes when we're trying to predict y, we don't predict it perfectly. And that's because sometimes we're not including variables in our model that we should, and so it ends up in our error term. Well, you might ask, well, Kristen, why wouldn't we include other variables? Well, there's a couple reasons. Sometimes you have so many things that affect y that you just try to pick the important ones. Sometimes you can't possibly collect data on every single variable. There's a lot of reasons, but we do our best to create a model that best predicts y, but that's also feasible in terms of time and money for collecting data. So let's continue with this. So the Greek letters, beta, these B's right here, Greek letters are parameters. So remember, parameters are represent the population. So these are the true values for the population. Well, we estimate them, right? Inferential statistics, we estimate our parameters using sample data and sample statistics. So we estimate from the sample these parameters, and then what we do is when we have these estimates, right, we can take values of x and plug it in to get an expected value of y, which is our next equation. So this is actually the simple linear regression equation, right? We estimate these parameters, we plug in a value of x to get the expected value of y. So this value right here, that means the expected value of y. That's what E stands for, and it's equal to the mean of y for a given value of x. So like I said before, we estimate these parameters, the y-intercept and the slope. We could plug in x for 17,000 students to say that, hey, for given x of 17,000 students, what would we expect y to be? Right, what would we predict it to be? So this is a simple linear regression equation. This is what we're trying to estimate right here. So this is, I know it's getting confusing, but this is the actual estimated simple linear regression equation. This is actually what we solve for. This is what we use. So notice now we don't have the betas, the Greek letters anymore. We have little b. But we still have 0 and 1. So 0 and 1 are basically whenever we have parameters that we're estimating, we number them. So this is 0, 1. If we had another x, a different variable, such as, like I said, availability of other restaurants, that would be x2. So its parameter would be beta 2. So then it would be b2. So we just number them. That's why it's sub 0 and 1. That's all that means. So what this equation is remember, these little b's are sample statistics, right? Sample statistics, right, are what we use the data for to estimate our parameters, our population parameters. So these are the values that we will actually estimate and solve for and get values for, that we can use to predict y hat. So this is called y hat, and it is actually a point estimator of EY, expected value of y. So this again is concepts we've heard before, where we have a point estimator, right? It's something that's a point estimator of some population parameter, right? We have our sample statistics, which we use to estimate our population parameters, right? So that's again what we're doing in regression. We collect data, right, to estimate our population parameters, to kind of get those values to figure out, what is really going on with our population, which is what we're really interested in. And of course, in this chapter, we will also not only estimate these parameters, but determine if they're statistically significant. So, for example, for B1, we could determine if the relationship between x and y, is it statistically significant? Meaning that if this is a positive 2 or whatever, is that statistically significant? Is it really something that's, is there really a relationship that's more than basically 0 is what we ultimately test it and compare it to. So this is the idea behind it. So again, let's just review that with this figure. So this is our regression model, right? We have y, something that we're trying to understand, an outcome variable, and it's equal to the intercept, the y-intercept, which is beta 0 plus beta 1x. So this is the slope for x, and then we have epsilon, our error term. So all this variability in y that we can't account for with this regression part right here, right, that line, right, ends up in our error term. So the actual regression equation, right, the expected value of y, the mean value, is equal to, right, our intercept beta 0 plus our slope times x, b1x. These are unknown parameters. These are the population parameters. This is what we really want to know, because if we have those and we know those, then we can figure out what y is. But of course, we don't really ever know those, so we have to estimate them. So how do you estimate population parameters? You go out and you collect data, right, on x and y, x and y, x and y, and you take all those data and then you use them to estimate those population parameters using our sample statistics. So here are our sample statistics. It's still 0 and 1. Now instead of Greek letters beta, it's B and B, B0, B1. This is our estimated regression equation. So notice how it's estimated. We're estimating this regression equation. This is what we're ultimately interested in, right? This is the true population parameters, but we estimate it. So we estimate it using our sample statistics, B0, B1. And then just our outcome variable y now has a little hat on it. The hat means that it's something that's predicted. So based off of this, the predicted value of y hat, is right here. So, right, our statistics, our sample statistics, beta 0 and beta 1, provide estimates of our true population parameters, beta 0 and beta 1, which is ultimately what we are interested in. So this is the estimation process for a simple linear regression. I know it sounds a little bit confusing, but basically how this process works is we have to figure out this estimated regression equation. And that's what we're going to talk about in the next video, right? Okay, Kristen, I get it. There's a line that we have to kind of estimate. How do we do that? Well, we have to figure out the intercept and the slope. If we can do that, then we can start using our regression equation to predict y, which is what we'd like to know. So that's what we'll talk about in the next video.